Welcome back. It is good to see all the friendly faces and some of the unfriendly ones this morning as well. We're continuing on the single cycle data path topic. This is our quiz Wednesday. I would like to push today's quiz to closer to the end of today, and I'll stop the recording at that point as well. We're not exactly behind at all, but I ask a very specific quiz question that will be very clear after today, would have been somewhat confusing before the first half of today. So we will do that closer to around 9:30. So and that's okay. It doesn't have to be in the very beginning of our Wednesday session. Where we left off on Monday, and I talked a lot about it being, in a sense, a bit of a review. What we're covering in this topic, which is taking the functional elements that we've already been building up towards the memories, the register files, and the ALU, and understanding how all the different instructions that we need to support in the single cycle implementation need to sort of coexist with each other. And that this is where we left off on Monday. Just that understanding that when we have multiple drivers or multiple signals that have to connect to the same resource, that's where our add a mux philosophy really does come into play. There's many such examples of it just on this diagram itself, but one way you can consider that would just be to look at, for example, the second input to the ALU and realize, well, I have both potentially the register value that I want to actually connect. Let's get this working here. I have the register value I want to actually connect, and I have the actual immediate input that I want to connect in, and that's why I have that mux there. And the reason we're not belaboring the point too much right now is because potentially you've already built that, or at least you were supposed to have already built some version of that for your lab number 4, right? So we already had at that point a component that allowed us to do regular add instructions, and that mux was there to determine whether or not we actually want the register value as our second operand or whether we wanted it to be an immediate instead. For our data path in the single cycle processor, we're supporting both. We know that for any given instruction, we either want just one path or the other. That's our if condition, right? If it is an R type instruction, we want that default path of register output to the second input of the ALU. Because for all of our R type instructions, that's what's expected. There's an RS and an RT field. We use those to read from the register file, and that's what's our input to our ALU. But then we have all those I type instructions, which includes things like our add immediate, but also things like our load and our store, in which we actually are encoding that 16-bit constant in the instruction. That's getting peeled off the instruction field, and that value gets sign extended, and that's the value that we actually want to connect to the second input of the ALU. It is at any point going to be either one instruction type or the other instruction type, and that's why we have that mux. So as part of our control structure for the processor, that's all that we're doing here, right? We're looking at certain information encoded directly in the instruction, and in doing so, we're generating a series of control signals from that information directly encoded in the instruction. And yours are going to potentially already look a lot different than the textbook version. Based on the Project Part A designs I already had the opportunity to take a look at earlier last night and earlier this week, everyone's ALU control scheme is going to wind up looking a lot different. And that's perfectly okay. I mean, that's completely acceptable. The textbook has one particular scheme they use, and they suggest a certain scheme for generating these values. You're definitely not going to need to follow that. For a lot of the other control signals that the textbook talks about being needed, like the one here for the second input to the ALU, or the one here for the input to the register write data port on the register file, you're going to probably have something that looks very similar to the textbook. My only suggestion may be to be very conscious regarding the names you choose for those control signals. They should have something that is human readable and meaningful to you and your team when you're able to look at that signal both in a spreadsheet as well as in a waveform as well as on a diagram. All of those three things you're going to have to be consistently connecting to each other, right? It's okay, my whatever instruction does not work. Let's look back on the waveform. Oh, it's because this signal should be 1 and in fact it's 0. Why is it a 0? Let's go back to my spreadsheet. It's this signal. It should mean this. We need to change my spreadsheet and change my control. You'll be doing that a number of times. You won't get it perfectly right on the first go. But otherwise, outside of some different naming conventions, and you'll have a number of additional control signals that the textbook doesn't need for the smaller set of instructions the textbook supports, it's going to look really similar to this design for your implementation. And that's our basic control scheme here, right? We wait for in our single cycle, we effectively wait for everything to quote unquote kind of settle down, right? Program counter to instruction memory to the execution of that instruction, and depending on how delays get modeled in our implementation, and for model sim and a behavioral implementation, it's just sort of the zero delta delays built into the simulator. All of those operations are happening in a combinational way from program counter read to instruction memory read to register files and control to execution and finally, and then we use those write signals along the clock edge to determine when to write to those sequential elements. So at the end of that cycle, that's when we write to the program counter. We always do that. That's when we write to the register file. We potentially do that if the instruction requires it. And that's when we write back to the data memory if the instruction requires that we do so. We talked a lot earlier in the semester about critical path in a general circuit. We can start to reason more about critical path in the single cycle processor implementation because it's the same concept. We have our clock cycle time, which is determined by whatever that largest delay is, that longest path through all the logic we have. That's our so-called critical path, ignoring some of the small implementation details about register setup and hold times. When we synthesize the design, we won't be able to ignore that anymore. It's definitely part of our analysis, but the tools also kind of do that analysis for us in that case. We know in general there's a critical path in any sequential circuit, any path between two sets of flip-flops in our design. For our single cycle processor implementation, and I'll bring it up here, we had previously talked about how in the single cycle processor implementation, load word is the critical path, right? And we were still hand waving this a little bit at the time. We were talking about critical paths in general and what has to happen inside a single clock period. But for the various stages of what has to happen, this is the textbook breakdown of the 5 stages of your instruction execution here, from fetch to decode to execution to an optional memory stage and then to a final write back stage where we complete the instruction. We have a path that actually has to go through and use all of those logic elements. And the instruction, and in fact, the only instruction that exercises the entirety of that path, that needs to take the longest route to get from program counter read to write back to the register file at the very end, is the load word or the load class of instructions. We can reason about every other instruction as being able to skip certain parts. Think about just an add instruction, just separate from this. Add has to read from the program counter, all instructions do. Add has to fetch from memory the actual instruction, as all instructions do. Add has to decode and determine what it is and potentially read values from the register file, as many instructions do. Add has to execute because it's doing the ALU work there. It's doing the actual addition there. Add does not need to use the memory stage at all. And in terms of what our design winds up looking like, as we kind of trace our way through this diagram for an add instruction versus for a load word instruction, for the add instruction, we have this memory happening here. But in terms of the critical path we could analyze for that instruction, we're avoiding it entirely, right? We're basically circumventing it. It's still part of our critical path in our design because those wires are still there, and we still have to get from flip-flop to flip-flop by traversing those wires and those functional elements. But in terms of which instruction is exercising that critical path, it's not add, for instance. But load word then becomes the only one that actually has to use all 5 stages of this processor. You may think, well, what about store word? Store word does a lot of these as well. We fetch a store, we decode a store, we do an add immediate type operation for our store. We use our memory for store to write to the memory file, but then we don't have to write anything back to the register file for store word. So store word can kind of end right here. It's only load word that winds up using all of those components along the way. It's a bit of a misnomer to refer to an instruction as being a critical path, but another way I think more correctly to phrase that would be the load word instruction is the instruction that has the worst case timing in our single cycle processor implementation. It's a very similar thing. We still would have the critical path there, but we have to design our processor to support the load word timing. And in the load word timing is there where we have to go through the most unit. That's the one that would have the worst case overall timing, which is going to set what we can run our clock frequency at for that single cycle implementation. This is a somewhat abstracted version of the view of what that worst case timing for the load instruction would look like. It's actually the same concept. This is just trying to show it by attempting to estimate at least abstracted real delays associated with the load word instruction from updating a value of the old program counter to the new program counter. We have our new program counter value. Finally, maybe there's some update delay here. We read from the program counter. We then update our instruction. We update our instruction. We generate all of our control signals. In parallel, we're also potentially accessing our register file values for our actual register. We then additionally have some delay associated with doing the arithmetic for the add immediate type operation required for our address calculation. Then we finally have some data memory access time, and we have to actually update the register file at the end of that clock cycle that we have there. That is the only instruction class that's going through all of those stages. So that's why we somewhat colloquially refer to load word as being the critical path instruction. But it's the instruction that goes through the most logic, so it has the worst case timing compared to the other instructions. We don't see this view of timing when we are doing our model sim simulation. We could have. We could have built these components with delays associated with them. That's a relatively straightforward thing to do in VHDL. And then you would see a version that has this basically a lot of incorrect results being calculated, right? The ALU output is only being shown as being valid at this part of the cycle, but it actually has some output throughout. There's some calculation happening in the ALU because it's always a combinational logic, taking inputs, generating outputs. It would be old values or potentially garbage values being computed until all these other delays have been satisfied, and we finally have both the register input we need and the immediate sign extended input we need for the address calculation to be correct. This would have been a valid way to do our model sim simulation. We have enough challenges in our design without having to worry about model timing glitches and things of that nature. When we get to the point where we're then synthesizing our design, those timing information then gets annotated associated with the individual components that we have there. And you can do, and I showed it very briefly last week, you can do a post-synthesis simulation or even a post-place and route simulation, which would be the lower level components and their actual timing delays associated with it. That will let you see your critical path as you're actually simulating the design. From our purposes, being aware of it is sufficient, not actually being able to see it as sufficient. So we've covered a little bit in earlier lectures about what it would mean to add that control to our diagram, right? Up to this point, the control signals are just kind of floating in there and connecting to muxes. For your existing implementation, we are just manually setting those control signals. We're pretending to be those instructions. If we know it's a load word, we're setting the appropriate muxes and ALU control, and we're doing all the things that would correspond to a load word. But we know it's actually in the instruction encoding itself that dictates that mapping between things like our opcode field and our resulting control signals in our design. And that's why I keep talking about the lookup table based approach or um, the Excel spreadsheet based approach to designing our control. The nice thing about MIPS, this is part of the MIPS design philosophy, is that so much of that information can just be directly encoded in those 6 bits that we have there. There's other information we have to potentially look at, but those 6 bits are a really good starting point. It does limit the total number of unique instructions we can potentially support, but we at least have that simplicity of looking at those 6 bits of opcode That then tells us a lot about what the instruction needs to do. It's always in those 6 bits. So we have an instruction field coming in, and we can just peel off those 6 bits, and no matter what kind of instruction it winds up being, those 6 bits will tell us a lot about the underlying control. We also know that for other instruction types, including for the R type is the most common case, there's other fields we sometimes have to look at as well, and that's the function field for the R type instructions. All R type instructions are very similar, right? In terms of how data flows through the system, they all do essentially the exact same thing: read from the registers, do some ALU operation, restore the result back into the registers. The only thing they have that distinguishes an AND from an OR instruction is what the actual ALU operation is going on. Everything else is exactly the same. And that makes our control scheme very nice in terms of a two-layer approach. We look at the opcode, and in looking at the opcode, we can quickly determine if it is an R-type instruction, and we set all those other control signals accordingly. If it is an opcode, and you can model it in your logic with an if statement, if the opcode is 0, and you can model that as an if statement in your logic, if the opcode equals 0, which corresponds to our R-type instructions, then also look at these least significant 6 bits and let that determine what that ALU control module needs to be. And that's considered sort of a two-stage control scheme where you always look at the opcode and then you alternately occasionally look at the function code if your instruction has a valid function code associated with it. The textbook does show that two-stage scheme, and that's what this diagram is attempting to reflect here. Um, Whether that is one module or two modules doesn't really matter. Um, I think it's easier just to think of it as just one module that takes as an input the instruction or the appropriate fields of the instruction and outputs all of the control needed for your processor. The textbook spends a lot of time talking about a very specific two-stage encoding scheme in which, given this function code field value, you get this resulting ALU op value that you can then use to dictate your ALU control. That doesn't map so well to how we've been doing things even with Project Part A, in which everybody has a different ALU implementation. Everyone has a different set of control signals they've named and used for that. And the slides do talk about what that scheme winds up looking like. That here's a scheme where all zeros corresponds to and 0001 corresponds to or. It doesn't matter. What matters is that there needs to be some sort of encoding scheme, and you and your project partner or partners need to agree on it. And it doesn't matter what it is; you just have to all be in the same understanding and shared understanding that yes, this is our ALU encoding. Add corresponds to this, and corresponds to that. Otherwise, it doesn't matter. And don't I would even say don't even attempt to implement the direct textbook version of the control scheme because what the textbook starts to talk a lot about, and let me see if I can find exactly where that's shown here on the slide here. The textbook starts to talk a lot about how we can do an efficient sum of products implementation of that ALU control scheme, given a look at the function fields and that in underlying ALU op implementation encoding strategy. From my perspective, that's not necessarily meaningless. What they're doing there, that's much closer to the 281 approach that we don't need to use at all, in my opinion. Right, our approach is the spreadsheet approach, which is opcodes and function codes as our rows of our spreadsheet, all the different encodings we have to support for our instructions, all the control signals we want to generate, including the control signals that dictate whether it's an add or a subtract or an or operation. Treat it as a large switch statement or case select statement in our VHDL, and then let the synthesis tools take care of that for us. And I think that's the smarter approach. This optimization, which is nice, you can really minimize the number of gates required, is also very brittle, right? As soon as you realize 2 weeks into project part B that you actually encoded one of your control signals incorrectly, and what should have been a 0 for this instruction is actually a 1 for that instruction, then you have to go back and re-optimize all that logic manually and get back to a new optimized sum of products representation. Um, that seems really unnecessary to me. And so our approach, which is don't really try to optimize at all. If you and your partner can't agree if it should be one signal or two control signals, well, make it two control signals. And even if one of them is technically redundant, it's okay. The synthesis tools will be able to detect that and kind of eliminate the one in your actual underlying FPGA implementation. What is important is that shared understanding of from from instruction to spreadsheet to schematic to what that control scheme winds up being for those instructions. And that's why when you look at project part B, we spend a lot of time working on that spreadsheet, with your team, getting to some shared agreement and understanding that we don't want to prematurely optimize anything because no matter how much time you put into it, and so at some point you do need to move on as well, no matter how much time you put into it, you'll get something wrong, and that's okay. And you'll only detect that through some thorough testing, and then you have to kind of tweak your spreadsheet and tweak your control logic.vhd implementation. But then it's not so bad because it's just changing some ones and zeros in that file. You're not starting over and re-optimizing the entire thing. So there's our almost complete data path with control, and the goal would be for at this point of the semester you should be able to then look at this version of the chapter 4 data path for the single cycle processor. And you may not have any of it memorized. I completely understand that. You should be able to work your way through this diagram bit by bit and understand what it's attempting to do and why those control signals are there and what their purpose is and what their value should be for various instructions. Nothing's really changed in this diagram from the previous version. The only thing that's happening here is it's explicitly showing the control unit, and the textbook treats it as two separate control units, but explicitly showing the control unit as a separate component that is feeding in the instruction fields. And again, here it's doing it as two separate components. Just treat it, I would recommend just treating it as one component in your design that takes the opcode in the function fields and then generates those various signals. We don't always show this in our design because it makes the diagram look pretty messy, right? There's just a lot of wires going on, and you're just connecting those all. In your own diagram, I would just recommend, labeling as it was previously the control signals next to the muxes in which they're being connected, and just be very clear with what your actual naming convention is going to be. David, you asked a good question here. That is something we're going to have to wrestle with a little bit. How do we reset the program counter? Um, that really depends on a lot of other things happening in the system. So, from the perspective of our instruction memory, at least implemented in our lab, we're going to be initializing that instruction memory exactly the same way you initialize the data memory for lab 4. We have a hex file, which will correspond to MIPS assembly instructions. There's a command in ModelSim to initialize that memory storage via that hex file. And from that perspective, it'll just start at address 0. So you would need like a reset pin on that register for the program counter. It does turn out to be the case, though, that as we talk about the MIPS ABI and what kind of standard conventions there are for things like memory layout, that there is an assumed starting initialization point for the program counter. And so at some point in project part B, you're going to want to then initialize the program counter to that value. It's I think it's 40 million hex. I don't remember the exact value there. It doesn't change our implementation because we don't have nearly that much memory anyway. We're going to have support for 1,000 or 2,000 instructions in our instruction memory. So we can initialize the program counter to a really high address. We're still only going to be grabbing the lower end bits for our read address, just like for lab 4 we had to do the same thing because yes, it's a 32-bit address we're generating. We don't want to have to simulate 2 to the 32 bytes of memory. We could, it would just be exceptionally slow. Everything's slow enough this semester. Before we jump into the quiz, let's do a collective quiz, which is basically asking the same questions, which is just tracing these control signals and what they're supposed to be doing. Again, the naming really does matter, in my opinion, and the textbook is okay for some and maybe less good for others. Branch is probably not a terrible name. in the designs I like, it's called something like is branch instruction. Right? You don't get penalized by the number of characters you use in your signal names, right? That's a signal that gets generated that tells your TA tells your partners in your project that yes, the signal only should get generated when it is a branch instruction. The textbook calls it branch. That's fine. ALU source. I don't really like that name at all. It could mean lots of things. What is an ALU source? I would call that ALU input B reg or immediate, something like that, right? You look at that name, and there should be very little, um, very little confusion as to what that ultimately means. And never manually type in your variable names or your signal names. Always copy paste, so you never have to worry about how many characters they are and how many typos you have along the way. Register write probably is okay. Mem write is probably okay. Even mem to reg is probably okay. You just have to be careful when you name these signals that you know what 1 and 0 corresponds to via the name. At least I think that's the case. So mem to reg is an okay name for that signal if you also make sure that as you input into this mux, it's the one input of that mux, right? The if select bit is 1 is what I mean when I say that. That corresponds to the data memory value going back to the register file. If you had these two inputs swapped, then mem to reg, in my opinion, isn't a good name for that signal. Then you'd want to call it not mem to reg, or you'd want to call it, ALU to reg instead, right? And I think that's an important consideration. The nice thing I believe is it's very easy to change that in your design. If you've decided that the signal's a little confusing, swapping inputs to mux is, a 10-second fix by and large, and you should be able to do so. Um, this one is probably the worst named one in my opinion. This is reg destination, and we've already run into this a little bit based on how load word is encoded, in which there's no RD field. Instead, it's using the RT field for my destination address for the right address in our register file. I would call that RT or RD or something like that, because that's literally what it's doing. It's selecting between those two fields and determining which one is actually the right address of those 5 bits. And for I type instructions, it's encoded differently than it is for R type instructions. And so could also call it R type or R to I type, but that's describing the instruction more so than it is describing the actual the actual control signal and what it's doing. So let us collectively give this a try, and then we can jump into the quiz here. So this is the spreadsheet approach. Let's attempt to do it together and see how it goes here. So what we would have is for our various instructions, we would have something that looks like this. Yours will have more columns and more rows, but conceptually it's doing the same exact thing here, right? So for the main control unit, which again, we'll probably just have one control unit, but ignoring the ALU side, we should be able to figure out, given what is in those 6 bits of the opcode, what the value of all those signals should be. So we can do this via Zoom chat because I know a lot of people aren't in the mood right now to speak up, and I understand that. Let's go row by row. It's not really clear to me as you're designing this with your partner um, which approach is better, going row by row or column by column. My guess would be row by row to start with, and then as you add new control signals that you didn't previously have, then you'd want to go column by column to confirm those control signals. But it's not really that clear to me. What is the quote unquote correct way to do it? Um, let's start with that first row then. If it's an R type instruction, and this is a little tricky for me to navigate here because you really do need to look at both this diagram and this slide at the same time here, right? So we'll start with, and you'll see me kind of skip back and forth quite a bit here. So for our R type instructions, I'll start us off because I mentioned that's the one that's got probably the worst name of all these instructions here, which is our register destination field. That is, are we taking the RT information as our right address, or are we taking our RD field encoded in our instruction as our right address for our register file? And you would just have to look at the green card to confirm, or look at Mars encoding of instructions to confirm. That looks great. That would be a 1 for that one. Let's go back here. Take my word for it because it's not. Okay, there we go. So there we go. That would be a 1 for that value that we would have there. What about for ALU source? I pose the question to you as the class here. For ALU source, um, for the R type instruction, should it be a 0 or a 1? Again, it may be most helpful to go back to the previous slide that shows what those signals are doing. So for ALU source, for our R type instructions, should it be a 0 or a 1? Good. I've lost the track of it here. It should be a 0, right? A 0 in this ALU source. And again, we talked about the naming convention enough. For your design, I'm not telling you you need this signal to be a 0. It depends on your mux. It depends on what you name that control signal, what 1 corresponds to, and it depends on what order you connected the inputs to your mux. At least for the textbook version here, or I guess to be more precise, the lecture slides version here, ALU source of 0, and that's what that 0 label here corresponds to, means we are connecting the output of the register file. Oh, this sucks. It connects the output of the register file. There we go. The output of the register file to the ALU. What about mem? And it's mem to reg. That is, are we taking the output of the memory and we connecting it back to the right data of the register file, or are we connecting the output of the ALU back to the register file? And it sounds like you've got it, where we are in fact connecting the ALU output. So mem value to reg, that's a no or a 0. Reg right, what should that be? And I can tell a lot of you have it, which is great. Okay, a couple of you have it. It's not clear that everyone has it, and that's fine. Register write, that's our write enable port on our register file. So that should be a 1 if in fact we want to write back to the register file. I'll figure this out eventually, guys. Okay. Mem read is an interesting one from this design's perspective. Our memory module that we've created doesn't even have a memory read port on it. We're always allowing it to read. For an R type instruction, let's assume we do have a read enable on that memory component. What should the value be for this, for an R type instruction? Seeing a couple zeros, a couple ones. I guess the problem is everyone entering zeros and ones. I lose track of what it's for. But that's fine. Well, the interesting thing about a couple of these is we talk about how we have to be very careful when we change processor state. We should only be updating the register file when the instruction dictates that we should, right? But for our reading of state, reading from the register file, reading from memory, the truth is, at least for this design and our relatively ideal view of what's happening in memory, we don't necessarily care whether or not we're reading from the memory. Definitely, I think we would agree that memory write would be 0. We do not want to write to the memory file for this instruction. I would allow, in terms of a valid answer, certainly 0 is correct here for this. It is correct. It's fine. We don't want to read. You're not getting it wrong. But also, I would argue that X is a valid answer here as well. Not X as in multiple drivers on our signal, but X as in don't care. We don't necessarily care what the value of memory it is. Read from memory, don't read from memory. From the R-type instructions perspective, who cares? And then for branch, it's not a branch instruction. And again, a better name for that signal would be is a branch instruction. That one, I would argue, you're working on your spreadsheet, you're working on this signal, and you realize, oh, yeah, it's definitely zero. And not only is it zero, it's 0, 0, 1, right? So that's what I was talking about. Whether you're going row by row or column by column, I think when you have a signal that's that clear and it's corresponding to whether it is a branch instruction or not, maybe that one you just do the whole column because it's kind of a one-off control signal specifically to support a very specific type of instruction. Let's go through the second row here. For load word, register destination, and this is again the lecture slide encoding of that particular mux. It's at least we know that it's different than for the R type. It's a different field, so that one's a 0. What about for ALU source? For the load word instruction, ALU source was, is second input to ALU a register or is it the immediate field instead? And absolutely for the L load word, store word, for anything that's I type, that's going to be a 1. Mem back to reg is also going to be a 1, right? Because we are writing from the memory back to the register file. That's really the whole reason that signal exists, right? And you could also now argue, well, yeah, obviously that signal is there to support the load word instruction. We could talk about whether that's a 0 or a don't care for that. If we're not writing back to the register file at all, we don't really care what the value of that mux is. Because load word, while it does write back to the register file, stored word doesn't, and branch certainly doesn't. If we're not writing back to the register file at all for store word, I would say technically the correct answer would be, we don't care. We don't care what the control signal is for that mem to reg mux. It could be a 1, it could be a 0, and it doesn't matter to us. Literally, we don't care, right? Or from a logic optimization perspective, we don't care. This looks terrible. If it's a 0 or a 1. Take the ALU output or take the memory output. I don't care. I'm not going to be writing that value back anyway. Memory read, certainly that's going to be our one case here. And for the others, I think the argument can be made it's also kind of a don't care condition for that. Memory write, we definitely do care. We only want to write to our memory when the instruction requires it. And unlike for our R type, where our ALU operation would be, check the function code. For the load word, our ALU operation, however you choose to encode it, which is going to be, I think, different for almost every single project based on what I've seen. For these two, it's going to be an add, right? Our load word requires our ALU to do an add operation, adding that base register to our sign extended immediate. But for branch equal, and we've talked about this only a little bit, and you have a couple weeks to really get on top of this for your implementation, the best way we have to implement our branch equal and our not equals is by instead treating that as a subtraction operation instead. One way at least. There's other ways we could do it, but one way at least, and the textbook way, is to determine whether or not two values are equal to each other or not, is to subtract them from each other. And if the result is 0, hence that 0 flag output you have in your ALU for project part A, that would correspond to our equal condition. Likewise, for branch not equal, we would just have to invert that output and use that as to whether or not there's going to be a branch. And if we look back on our diagram for branch, that's exactly what's happening on this diagram here, right? We are confirming that two things are the case for us to actually take that branch. First off, there's all that somewhat convoluted looking logic for calculating the branch target offset. It's PC plus 4 already, plus the shift left logical to immediate encoded offset to get our potential branch target new PC value. And we have that mux there. This is kind of an internal signal. This is not strictly generated from your opcode. We only take this signal. We only take our branch if it in fact is a branch instruction. And this, from the textbook, that means is a branch equal instruction. You'll need one for branch type of some sort, but is a branch equal instruction and the output of my operation corresponds to a 0, meaning input A and input B of my ALU are the same. They subtracted from each other, we get a 0 result back out. We'll continue with versions of this exercise on Friday. Don't disappear yet. I'm going to stop just my recording right now, and then we can just all go to Canvas and do our quiz for today, which should look pretty familiar from what we've been doing in class. It's covering essentially the same exact topics. So I'm going to end the recording right now, but then please do stick around. Don't leave, and we'll do our quiz right now as we open up Canvas.